Greetings. Dear student, in last lecture, we learned about moment distribution method and stepwise procedure to analyze indeterminate structure using MDM. In today's session, we'll solve a numerical using the MDM concept. The statement of numerical is analyze the beam shown in below figure using MDM. Also draw the shear force and bend moment diagram. The given beam is a continuous beam of two span AB and BC. Span AB is of length 4 meter and having a moment of inertia I, whereas span BC is of length 3 meter and having a moment of inertia I. Within the span AB, a point load of 50 kN act at the mid span, whereas the span BC is subjected to a uniformly distributed load over the entire length of magnitude 10 kN per meter. The very first step in the analysis is to find out the fixed end moment. For this, we'll assume that ends are being locked, and that's why we can analyze the beam into two standard cases. The span AB fixed at the end and subjected to a point load at the mid span, and the second span BC fixed at the end subjected to UDL for the entire span. If I talk about the fixed end moment, the fixed end moment at the end A can be worked out as minus WL by 8, which equals to minus 50 into 4 divided by 8, which gives an outcome of minus 25 kilonewton meter. Whereas if we calculate moment at B, we can get it by the relation plus WL by 8. If you substitute the value of load, the value work out to be plus 25 kilonewton meter. Now if we talk about the beam B to C, we can get the moment at the end B, which is given by the relation WL square by 12. If I substitute the values here, minus 10 into 3 square divided by 12, minus 75 kilonewton meter. Whereas at the end C, we will have the moment WL square by 12 plus WL by L square by 12, which work out to be plus 7.5 kilonewton meter. After finding the fixed end moment, the second step is to calculate the distribution factor. The distribution factor is uh, estimated at the joint which is being subjected to a rotation and which is having a certain degrees of freedom. In our given structure, joint B is a joint which is having a capacity to rotate. And at this joint, the two members are going to meet. So we have to find out what relative stiffness they have here so as to carry the rotation applied at that particular end. So at the joint, if we want to find out that relative stiffness, we will utilize the relationship which is tabulated here with the very first column of the table is joint, the second column is member, the third column is length of the member, fourth column is moment of inertia of the member, fifth column is the stiffness of the member, sixth column is the cumulative stiffness, or we can say summative stiffness. Then the last column is the distribution factor, which is the ratio of the stiffness, individual stiffness of the member versus the total stiffness of the joint. So it will be better if I talk about this cumulative stiffness as a joint stiffness. So joint B, it is a common joint having the two members contributing towards the rotation BA and BC. Length of the members has been mentioned here 4, 3. Moment of inertia is I. Since the joint has a far end as a fixed, that's why absolute stiffness will be worked out as a 4 EI by L. If you substitute the span, it will be 4 EI by 4, which results in a value of EI. Similarly, the member BC is there, which is of length 3 meter, having moment of inertia I, and far end that is C end is fixed. That's why we are getting absolute stiffness as 4 EI by L. 4 EI by 3, the resultant value is 1.33 EI. If I take the joint stiffness here, it will be the summation of the stiffness of the two member, which work out to be 2.33. If I want to have a distribution factor, it is the ratio of individual as absolute stiffness versus the joint stiffness. We can say it is the EI divided by 2.33 EI, which work out to be 0.43. Whereas for the member B to C, it will be 1.33 EI divided by 2.33, which comes to be 0.57. So if I add these two values, 0.43 and 0.57, it is resulting into a value 1. Okay. Next step number 3. After doing this, we will perform the moment distribution. For this, again, we will refer a tabular format where the very first row will be about the joint. We will consider all the joints which are available within the span. of the beam A, B, and C. Now members at joint A, member AB is there. At joint B, the member BA is there. Since it's a common, we have one more member meeting at this one, B to C, and at joint C, C to B member is there. And if I talk about the distribution factor for the joint A, is there will be no distribution factor since it is a fixed joint. At joint B, we'll have the BA contribution as a 0.43 and BC contribution as a 0.57. Whereas C joint is fixed, that's why no contribution will be there. Now, fixed end moment is the next row, where we will put up the fixed end moment at the respective ends. That end A we got minus 25, at end B towards the span B to A is plus 25, at B towards the span B to C it's a minus 7.5, whereas at C we have got plus 7.5. Now we'll do the moment distribution. What's the meaning of this moment distribution? We are going to take equilibrium of the moment at the joint here. Means here I will take a MFAB, MFBA plus MFBC is equals to 0. So I will take a balancing of this one. I will see what is the net balance for this. So it can be worked out as of 25, the clockwise here, minus 7.5, anti-clockwise here. The answer is 17.5. This is the balance moment which we need to be distribute among the members. So distribution about the member BA will be equals to 0.43 multiplied by 17.5, but taken in opposite direction. Means here I'm going to get positive value, so I will multiply it by negative value to balance it. The minus 17.5 I have taken. That's why the workout to be minus 7.525 kilonewton meter. Whereas distribution for the span BC will be equals to 0.57 into minus 17.5 comes to be minus 9.975. This distribution I have written here. The next task will to perform the carryover. Since and A is fixed and C is fixed, the carryover moment has to be transferred to this end. So the carryover transfer will be the half the moment at a particular joint to the far end. It will be zero point 0.5 multiplied by 7.525. It comes to minus 3.7625. And the second transfer will be towards the joint C, which is fixed here. Again, half of the minus 9.975 will be transferred to this, which is about 4.9875. Now, after doing this, what we'll do, we'll take a balance again, once again. So when I have taken a balance here, if I add the moments here at this particular joint, that joint for the BA section, I'm going to get 17.475, and for the joint for the member BC for the joint B, we are getting minus 17.475. Plus and minus this result that there is a complete balance of the moment here. That's why the further iteration can't be possible. So we'll stop here and we'll write final moments for this particular iteration. So here I will do addition of all the moments within the column AB, within the column BA, within the column BC, within the column CB, which will be the final moment for the generated due to span loading at the particular ends. So we got here MA as a 2.87625, MBA 17.475, MBC minus 17.475, and MCB as a 2.5125. Once we know the moment, the next task is to find out shear force and bending moment distribution. For taking shear force and bending moment distribution, let us consider the mechanism at individual span like this. They are taken the span A to B. The fixed end moments which we have received from the calculation has been put at the ends. The applied loading is there. Since ends are being locked here, there will be reactive force RB. At the end B, there will be reactive force RB1. If I take equilibrium of vertical forces for this particular session, we'll get the relation RA plus RB1 equals to 50. Now, what is meaning of RB1 here? Since joint B is common between the span BA and BC, so there will be reactive forces from both the spans. That's why first span I'm going to say it is a B1 contribution, and for the second span I'm going to consider it as a B2 contribution. Now, if I take moment about the joint A, the moment will be considered like minus 4 times of RB1, means the anti-clockwise moment due to reactive force, minus 28.28 the moment at the end A, plus 50 into 2 the moment which is caused by the point load going downward in a clockwise direction, plus 17.475 the moment at the end B. From this we get RB1 as a 22.17. Back substituting this value in the previous equation which we have received from summation of Fy, we can write RA equals to 50 minus RB1. So it comes to 50 minus 22.17, which comes to be 27.83 kilonewton. Now we'll go to the second span B to C. We'll substitute all the values which we have received from the final end moments. At end B, we have got received a moment of 17.475, at C 2.52, and 10 kilonewton is the UDL over the span 3. If I take summation of forces, vertical forces, it will be equals to RB2, there's a secondary contribution of reactive force from the span B to C, plus RC is equals to 10 to 3, 30. Now, if I take summation of moment about the joint B, so it will be minus 3 into RC, the anti-clockwise rotation for the reactive force RC, minus 17.475, the moment at the end B, plus 10 into 3 into 3 by 2, the moment caused by the UDL, plus 2.51, the moment at the end C. So from this we get RC work out to be 10.02 kilonewton. Now we'll do the back substitution of with reference to the summation of forces in vertical direction for span BC. We get 30 minus RA is a resultant value of RB2, which comes to be 19.98. Now RB we are getting from both the span, that's why we'll add RB1 plus RB2 to get a final value of RB, which comes to be 42.15, means the addition of 22.17 plus 19.98, it comes to be 42.15. Once we get the reactive forces, we can prepare a shear force distribution diagram, which work out to be like this. At end A, it was 27.83, then 50 kilonewtons comes downward. That's why it changed its sign to 22.17. Then reactive force comes here, RB. That's why it again changed sign to 19.98. The UDL is where there. That's why it goes in a linearization part, and it comes to be 10.02. Finally, at the end C, we got a reactive force as a 10.02. That's why it come back to 0. This is the shear force diagram for your given continuous beam. Now, if you talk about the bending moment diagram, it's nothing but a variation of moments which we have received at the ends of the beam. We have received this with reference to fixed end condition. So MAB, MA moment at A was 28.77, MBA and MBC was worked out to be 17.475 in opposite direction, whereas at the point C we got at 2.51 kilonewton meter the moment. If you overlap the free end moment diagram with this fixed end moment diagram, so we'll get a envelope which will said to be integrated envelope or balance envelope with reference to free end moment and the fixed end moment. This balance envelope, which is given in the sign minus plus, will be called as a net bending moment. Now, how to get this free end moment? We know for the load which is at the mid span, we have a relation WL by 4. The W was here about 50, 15 to 4 by 4. It comes to 50 kilonewton meter here. Whereas in the case, the second span, we have a distribution with reference to UDL. So the relation we have for free end moment as a WL square by 8. If I put the substitute the value there, that load was 10 into 3 square divided by 8, it can work out to be 11.25. So likewise, we can get the bending moment profile for the given continuous beam. That's the end for the numerical. Hope you understood. I will be coming with much more numericals on the basis of slope deflection method as well as moment distribution method in upcoming article. Till then, goodbye.